Sample exam 5, problem number 1. If a normal distribution with mean mu and variance sigma squared greater than 0 has 46th percentile equal to 20 sigma, then mu is equal to. Sample exam 5, question number 1. We're given that 20 sigma is the 46th percentile, and what value of is mu. Well, if we were to convert this to the standard normal, that point would go to -1/10. And to convert that, you subtract the mean divided by the standard deviation, which is this, and that is equal to 1/10. Well, now we start solving for mu. Multiply both sides by sigma. Take mu this way, take that quantity this way, you get this. Factor out a sigma, you get 20.1 sigma is mu. Number 2, suppose u and v are independent random variables, each uniformly distributed on the interval 100 to 200. What is the number t for which the probability that at least one of u and v exceeds t is 1/4? Problem number 2. We're given that u and v are distributed from uniformly from 100 to 200, and based on that, since they're independent, the joint density is the product of the two, and we want to find the probability that at least one of them is greater than t. So that means it's this shaded area here. And so one strategy is to take, since this whole area must integrate to 1, we can take 1 minus and find this little piece here. Otherwise, you have to find the probability that u is greater than t, that v is greater than t, and then subtract out this quantity because you added it twice. But we'll just do the 1 minus, and that goes from 100 to t in both directions, which is this. Integrate with respect to u first. We get u, plug in the limits of integration. Integrate with respect to v, which then you get a v, plug in the limits of integration, you get this squared, and they said it was 1/4, so you start solving for t, square both sides, take the 100 over, you get t is equal to 100 plus 50 times the square root of 3. Number 3, which of the following must be true for an unbiased estimator of a population value? So in number 3, it asks which one is true. Well, for number 1, the estimator does not have to converge to the parameter. And as simple as, if each individual x is if you take the expected value, you get the mean, but as the sample size increases, it doesn't converge to the mean, where like the sample mean does. It converges in probability to the parameter of estimate. So based on that, number 1 is false. And then for number 3, any estimator that has an asymmetric distribution makes this one false. If it's asymmetric, it means the probability of being on one side or the other is not the same. So an example is s squared, the unbiased estimate of the sample or the variance is a chi-squared, which is not symmetric. So the probability of being more or less than this is not the same. But the probability, but statement number 2 is correct, and that the expected value always equals the population value. Problem number 4. If x, y, and z are 3 events such that the intersection of x and y equal the intersection of x and z equal to the empty set, but the intersection of y and z is not the empty set, then the probability of x union y union z must equal. So number 4, we're asked to find this probability, the intersection of the three. And the formula is you take the individual and then you subtract the pairwise, and then you add back the three-way interaction. And but these are the empty set. So then you're just left with this. Number 5, suppose the joint density function for x and y is given by f of x y equal to 3/4, where 0 is less than y squared, which is less than x, which is less than 1. What is the marginal density function of x for x between 0 and 1? Problem number 5, we're asked to find the marginal density of x. But you have to be careful in the for the limits. It looks like they're both greater than 0 and less than 1. But it says that it's y squared is between 0 and 1. So really y is between 1 and -1. And so the area is this region. So you have to be careful. And that's why I like drawing a picture of the region that we're integrating over. So to integrate out y, we have to go from this point to this point, which is plus or minus the square root of x. So then when you integrate the density of 3/4 with respect to y, you get this, plug in the values, you get 3/2 times square root of x. Number 6, let x1 through xn and y1 through yn be two random samples from independent normal distributions with variance sigma squared, the variance of xi sigma squared, and the variance of yi 2 sigma squared for I equals 1 to n, and sigma squared being positive. If u is equal to this quantity and v is equal to that quantity, then which of the following is true? So number 6, it's asked to find, well, let's do a little background first. So u divided by the variance, population variance, is chi squared n minus 1. V divided by its variance, which is 2 sigma squared, is chi squared n minus 1. So if we were to add these two quantities, then we know it's chi squared 2 times n minus 1. But to add these, you get a like denominator, and you add and you get this. And so that's 2 chi squared times 2 n minus 1. Number 7, let x be a random variable with cumulative distribution function f of x is equal to 1 minus e to the minus x for x positive. What is the probability that e to the x is between 0 and 4? Number 7, we're asked to find this probability. Well, if we take the natural log of both sides, then this goes to negative infinity, and that's just the natural log of 4. And we're given the CDF of x, and that's what this is. So this is just f of natural log of 4. So you plug it in. Now the negative can go up to the 4, so it's 4 to the minus 1, which is 1/4. But the e and the log cancel, leaving 1 minus 1/4, which is 3/4. Number 8. Suppose Q and S are independent events such that the probability that at least one of them occurs is 1/3, and the probability that Q occurs but S does not occur is 1/9. What is the probability of S? Now, number 8, I think the trick is to utilize what they give, and then somehow that'll work out. And in this case, it's all you need. So to find the probability of S, we can take the probability of Q union S, which is this whole region here, but then if we subtract out Q union S complement, which is this piece, then we're just left with the probability of S. And it breaks down to 2/9. Number 9. Suppose y is a random variable with mean mu and variance sigma squared. For what value of a, where a is positive, is the expected value of ay minus a to the negative 1 squared minimized? So problem number 9, we're asked to find the a that minimizes this expression. And let's multiply this inner part out and we get this. And then we bring in the expectation. So that's a constant. So it's the expected value of y squared. And the minus 2 times expected value of y, which is mu, and then a squared. So now when we take the derivative of this with respect to a, then we're left with 2a expected value of y squared. And then that's a constant. So here, and then we get minus 2 times 1 over a cubed. We set it equal to 0. We solve for a. And then the answer writes it as a negative exponent. When you take it to the numerator, it's negative. And you could also take the second derivative with respect to this and note that it's positive, which then does indicate it is a minimum. Well, hope you enjoyed it. More to come. Please subscribe so you don't miss out on the next set of questions and answers.